All right, so for the quiz, which is going to be on Tuesday, what we did in chapter 2, section 1 was we said, okay, we learned about the derivative in chapter 1, which means slope, and then we said, well, how would we write equations for that? How could we put that into a more technical and formal frame of reference? And so what we did is this, we found this equation here, and the first part of it is slope. It's just the difference quotient part. The difference quotient part right here is the slope between 2 points. One is a plus h. This is just the slope between those 2 points. And then we said if we let h get really small, the 2 points get closer and closer together, become 1, and that's what derivative is a slope at 1 point, the slope of the tangent line. So we have the limit as h approaches 0. Now, some people had asked as we were doing it, well, what's this limit thing? Why do we have to do that? Why can't we just let h be 0? Well, what happens if you try to let h be 0? It's undefined, right? You can't do slope with just 1 point. And so if h is 0, this is undefined, but there is a limit. We know that as the 2 points get closer and closer together, that these outputs of this thing right here are the slopes, and they're getting closer and closer to some value. And that is the slope of the tangent line. So we learned about that in that section 1. So you need to be able to go through that and do some of those limit problems along the way. And we had some algebra that was involved that we had to do there. And then we used that in section 2, where we took the a here and we changed that to an x. And we said instead of doing this to find f prime at 2 or at 3 or at 4, how about if we do it to find f prime of x for any x? And so we changed those a's to x's, and we came up with this power rule, this kind of shortcut that we have. And we're going to learn many other shortcuts for derivatives along the way. Okay, but for right now, we have this. Okay, so we have this kind of this shortcut where we bring the power down in front and drop the power by 1 and so forth. So that's where we learned that. So we're going to be putting that to use. And then what we did in section 3, kind of starting yesterday, is we said, what is this limit business? Let's investigate that a little more, because this is such a key part of this thing, letting h go to 0. What is that all about, this idea of a limit? What is that? So we took a little side trip, I told you yesterday. We're going to take a little side trip here and work on limits. We're going to do that for a little while today. And then we're going to get back on track with this idea of derivative and what's going on here, okay? So we took our little side trip, and our side trip involves limits. And so here's what we talked about yesterday, okay? So we were saying, and not all of this, and some of this we're going to get into today. So we said, okay, if you've got limits, so just kind of put the idea of derivatives and that kind of thing out of your head for a little bit here. And we're just talking about this idea of limit problem. All right? And what we saw is we've seen some algebra type limit problems that we have to do. And that's what the worksheet was. Okay? The worksheet was some limit problems, didn't have anything to do with derivatives. Okay? Or slopes or anything like that. It was simply about limits. And how can we work those? Well, one way we can factor in, well, the first thing we do is we substitute, right? We substitute in. If the limit as x approaches 3, we plug in a 3. Okay? The limit as x approaches 2, we plug in a 2. So that's the first thing we do, and we hope we get a number. So what about this up here? Some of you are so busy writing here, I don't know if I'm getting anywhere with this. It's good to write this down, but look up here just for a second. So the first thing we want to do is plug in. So like this limit right here, what would the answer be? Right here. Yeah, easiest kind there could be, right? That's just a line, x plus 3. What that says is x is getting close to 2, the y values are getting close to 5. They actually are 5. So that's the easiest kind of limit there is. You just plug in a 2, you get a 5. But sometimes when you plug in, you get 0 divided by 0. And when you get 0 divided by 0, you keep going. The term for that is indeterminate. What that means is we cannot determine what's going to happen here when we have 0 divided by 0. It's a special kind of undefined. So we keep going. Well, what does it mean, keep going? Well, on our worksheet, it meant maybe we can factor and cancel. Maybe we can get a common denominator and cancel. Maybe we can multiply by the conjugate and cancel. Somehow we're hoping something cancels. Why are we hoping something cancels? So we don't get 0 over 0, right? So that we can then plug in and get our answer. Okay? Now, sometimes when we plug in to do substitution, we get 6 over 0 or negative 2 over 0. Well, then we say the limit does not exist. Okay? We say the limit does not exist if we get 6 over 0 or 2 over 0. And I mentioned this yesterday, somebody in the other class asked about, what if you get 0 over 4? What if the zero's on top? That's 0, right? That's it. That's your answer, 0. But if you get 6 over 0, 2 over 0, something like that, it does not exist. Now let's talk about that just real briefly. We're going to investigate that a lot more deeply in a later chapter. Basically, the reason that does not exist is there's a break. There's a vertical asymptote. Because here's what's happening. 6 over 0 really means infinity. 6 over 0 really means infinity. And the reason it means infinity is, think about what's happening. We're talking about x getting close to 0, or x getting close to 2. So what's happening is the bottom isn't 0, it's getting close to 0. Well, what happens if you take 6 and divide it by something close to 0, like 1/1,000,000th? Yeah, well, I mean, what's 6 divided by 1/1,000,000th? Really? Now, what is 6 divided by 1/1,000,000th? 6 million. Yeah, it's 6 million, right? 6 divided by 1/1,000,000th is 6 million. It's getting really big, is what's happening. So when you have 6, that's why 6 divided by 0 really means infinity. Because what it really is, what's really happening is it's 6 divided by something really, really little. And when you divide by something really, really little, you get something really, really big. Now you say, well, why didn't that work with 0 over 0? Well, that's a problem. You've got something getting really little divided by something getting really little. Which one is that? Well, this is why it's indeterminate. It depends how fast the things are getting little. If the thing on top is getting little a lot faster than the thing on the bottom, it might be going towards 0. If the thing on the bottom is getting little a lot faster than the thing on top is getting little, it might go to infinity. Or it might go somewhere in between. That's why it's called indeterminate. That's something we're going to get into a lot more later on. So we don't have to worry about that right now. But 0 over 0 means we keep going. 6 over 0, 2 over 0, we say does not exist. Because what's happening is we got a graph that's doing this. One tail's going up like this, another one's going down like this, or something like that. The cars aren't meeting. Cars are not meeting. And so the limit does not exist. All right, today we're going to do this later on. And then in your book assignment today, we did graphs. So when we do limits with graphs, we're talking about do the cars meet. The graphs are the easiest ones there are. The graphs are the easiest, because think of the video yesterday. Do the cars meet? If the cars meet from both sides, that's your limit. If the cars don't meet, the limit doesn't exist. We can talk about the car on the left, or we can talk about the car on the right. What are their limits? So when you have a graph, limits are pretty easy to do. When you're doing the algebra, like the worksheet, right, you got to be able to do that algebra. And then we'll talk about what tables mean later on. So that's our side trip into limits, and we want to be able to do those things. All right, then the last thing that will be on the quiz, then we're going to come back and bring this all back together. We're going to start this today. And what will happen is we're going to now come back to what we learned in chapter 1 with the chart and increasing, decreasing, concave up, concave down, local back, local in, all that stuff. And we're going to do it with equations now instead of with graphs. Okay? So we're going to take what we've learned with these derivatives and these shortcut rules that we have for derivatives, and we're going to use that information to do the stuff we did back in chapter 1. Okay? Plus we had that little side trip into limits and dealing with those. All right? And all those things will be things that you'll be asked to do on the quiz next week. Okay? All right. So, let's take a look at your book problems first. All right? And I think this can go quick enough that we can just... All right, so we can just whip through these pretty fast, I think. All right, so number 13. As x approaches 0, the cars would be meeting where? At a y value of 2. We're talking about right up here. The cars would come in right here, and they meet at 2. Limit as x approaches -3. The cars are coming together, meeting at -1. We don't care about that dot here. The diner is burned down. They build it somewhere else. Doesn't matter. cars come in, they're meeting right there at a y value of -1. That is the limit. As x approaches -1, it doesn't exist. The car on the left comes in here at 1. The car on the right's up here at 2. There's a break. The limit does not exist. Number 16, as x approaches 2 from the left. Let's don't be reading that weird. It doesn't say x2 minus whatever. That's x approaches 2 from the left. That's how we say that. X approaches 2 from the left, right up there at 1. X approaches 2 from the right, also 1. So therefore, in number 18, the limit as x approaches 2, here's 1. Whenever it says x approaches 2, it means from both sides. So both cars are coming in at 1. Left and right were both 1. Number 19, x approaches -2 from the left. Oops, from the left, right here. 0, 0. X approaches 1 from the right. 0, right? There's a break there, but we don't care. We're only looking at the car coming in from the right. The limit is 0. X approaches -4 from the right. Down here at -2. X approaches 4 from the left. Down here at -1. Now, on 23, they said f prime. Now, I told you that these problems didn't have anything to do with derivative. Well, just think of f prime as a function. It has its own y value. The f prime y values are the slopes of this graph. So when we talk about what they're approaching, we're going to talk about the slopes. So, as x approaches 3, what are the slopes here? -1. On this side? -1. So the y values of the f prime graph are -1 on both sides. So the slope, or the limit is -1. -1 from the right. The slopes are 0. So the y values of f prime are approaching 0. -1 from the left. The slope here is 1. So the y values of f prime will be approaching 1. And then x approaches -3 is this way. Slopes are 1 on both sides of that. So the y values of f prime would be 1. Very good. All right, now let's talk about 39 through 42. Now, on 39 through 42, and this could be something I could very well ask you about. You have this piecewise function. It's 3 minus 1/2 x squared when you go from -infinity to 2. And it's 3x minus 5 when you go from 2, and it includes the 2, to infinity. Now let's talk about this. Now, tell me what you guys did. What did you do to work this? Just plugged in numbers? I like that. You didn't try to draw a graph or anything? You don't need to draw a graph. Now, limits are easiest when we have a graph because we can think about the cause. Okay? So, I'm a little nervous that you might have gotten one of your answers by plugging in and gotten it right, and you got lucky. So let's talk about it here. 39 says the limit as x approaches what? 3. Okay? So what'd you do? You plugged in a 3 where? To the bottom one? Why the bottom one? Because that's where 3 is. It's from 2 to infinity. 3 is not part of this one, it's part of this one. So you plug the 3 in, and you got 1. Did I do that right? No. That's awful. What am I doing? 4. 3 times 3 is 9. 9 minus 5 is 4. Okay? All right. What was the next one? X approaches 0. So where'd you plug that in? Into the first one. And you got 3. Okay, very good. What's the next one? All right. Where'd you plug this one? Second one. And you got lucky. You got lucky. We'll talk about it here in a minute. What's 42? X approaches 1. And where'd you plug that? First one? 2.5. Okay. You got lucky. So if that's what you did, then I don't think you understood completely what's happening. On 41, you guys told me you did what now? You plugged 2 where? Into the bottom one is what you said, right? Because that's where it's included. Okay, that is bad. Well, it's bad in the sense it's half right. I heard somebody say, oh. What's that? You have to plug it into both. Now, let's talk about why, right? If you're not seeing that, right, now you're a little unclear what's happening. So let's think about what we got here. If we were to graph it, I don't think you have to graph it, but we should think about maybe what the graph might be. What would this be? Parabola, upside down. So one possibility is it might just roll along here, and then all of a sudden at 2 it would just stop like that, right? And then what would happen? Then a line would take off. Now, the key is, where does the line go? Take off? Does the line go like that? Or is it possible that our graph is this, and then the line takes off and goes like that? Now, does it matter? It matters in a big way, because if it's this, then what's the limit? It's whatever that point is, right? If it's this, what's the limit? Does not exist, right? So if the parabola is coming into 2, and of course we don't include the 2, but that just means there's an open circle, and then the line takes off. So this is the first time you're going to see this problem a lot. It'll ask a lot of different questions, but when you see it piecewise, a couple things you want to focus in on. Number one, where does it break? Well, this one breaks at 2. Those are the points we worry about, because you were right on these other ones. On 39, 40, 42, you were right to just plug in, because you knew you had a parabola and you knew you had a line, which are nice and smooth. Remember in the video, it said that there's a break there? The guy was saying, well, there's a break here, the limit doesn't exist, but there's a lot of other places the limit does exist. It exists over here and here and here, and the cars would be here, right? Well, that's what you're doing when you plugged in your 3 and your 0 and your 1. You were just on your parabola or on your line, and you know the limit's going to work at those, because the cars are going to meet, because those are just nice, regular old graphs. The only place we really have an issue is at 2. So what we needed to do is plug a 2 into this one, and we get 1. And we plug a 2 into this one, and what do you get? 2 squared is 4. 4 times a half is 2. 3 minus 2 is 1. Aha, that tells us we must have this situation. You don't need to know what the graphs look like. But what you need to know when you have a piecewise function is you need to plug that 2 into both pieces and see where the one ends and see where the other one takes off. And if they end and take off at the same spot, then they're connected. And that's where the cars would meet. So the cars are meeting at 1. But if we would have plugged, so you see why you guys got lucky. So if you'd have plugged a 2 into here and got a 1, but if we'd have plugged a 2 up here and got a 3, then we'd have been looking at this situation. They don't meet. Okay? Think about it. This one is from the left of 2. This one's from the right of 2. And that's what was happening. All right? So if you run into that one again, we would be aware of that. All right? Now let's talk about the worksheet. I'm not going to go through all of these, but we'll go through the answers, and I'll work out just a few things here. If you have some difficulty, I don't want to bore those of you that are fine with the algebra. You're going to have to do this algebra on the next quiz. If you need extra practice on this algebra, come see me. We can talk about it. Maybe I can find some extra practice for you or something. Okay, on this one, so the first thing we do is do direct substitution. So we plug a 2 into here, and we get 0 over 0, right? So you factor and you cancel, and you end up with negative 3 fourths. Is that right? At least that's what the other class said. You're wrong. This one, you plug in negative 1, and what happens there? You get negative 2 over 0, right? So that does not exist. Don't say undefined. You can say no limit, or say does not exist. Okay? Number 3, you plug in a 5, and I believe you get 0 over 0. So you factor and cancel, and you cancel the x minus 5s, and then you plug in your 5, and you get 12 over 0. Oh, so what's that mean? Does not exist. So sometimes that happens. You start with 0 over 0, thinking maybe there's a hole in the graph, maybe the limit's going to exist, like it did on this one. So this one, there's a hole at 2. This one, there's actually a vertical asymptote at 5. We thought maybe there was a hole in the graph, but it wasn't. It was a vertical asymptote. Okay. This one, we plug a 2 in, and we get, what is it, just about 5? Yeah, it just comes out 5. You don't have to do anything. It just comes out a number. So you don't want to factor it or anything. Well, you could factor it, but it would just be wasted effort, really. You could factor it, then plug in your 2, and you get a 5. But you could just plug a 5 in right off the bat. Okay, maybe it's faster to factor it than it is to square it and do all that. Okay, let's go to these at the bottom now. Here's where you get into the other algebras. We have the factor cancel things going on there. Here, when we see a conjugate or a radical, we're going to think conjugate. So we're going to do the top and bottom times this. Now put parentheses around those because this is a FOIL situation. Now, one other conversation I had with a couple of you. When you get to this kind of this conjugate thing, one of those you want to FOIL out, but the other one you don't. Which one do we want to FOIL? The bottom, because it's going to have the outers and inners drop out. That's why we did the conjugate. So when I do root x times root x, that's just x. The outers and inners are going to drop out. -3 times 3 is -9. So that's what we want to do with the bottom. The top we do not want to FOIL because we're hoping something cancels. Now it looks like we can, except not quite. Why can't we cancel those? Well, they're not the same. What can we do? Take out a -1. So if I take a -1 out of that top thing, then it becomes -9 plus x, which of course is the same as x minus 9. And so we have that, and we have that. On the bottom we have x minus 9. Now those cancel, and so we get this. Now we can plug in our 9. Don't forget, that's the whole point of doing this, is we like to see what's happening when x gets close to 9. So we want to plug a 9 in if we can. And so we plug a 9 in, square root of 3 plus 3, or square root of 9 is 3, 3 plus 3 is 6, times -1, we get -6. Okay, I'm not going to do number 6, but it's the same thing. You're going to take this radical plus radical 12, and this radical plus radical 12, and you're not going to want to distribute the top, but you will want to FOIL out the bottom. And you end up with x squared here. I said I wasn't going to do it, and then I ended up kind of doing it. But when you FOIL that, it ends up being that. So those things cancel, the x squareds cancel. Now you're ready to put a 0 in for x. So that's how a conjugate looks. That's how a conjugate works. And the answer to that was like 2 root 12, which would reduce to 4 root 3. I don't care. You can give either one of those answers. It's fine. Okay? All right, let's talk about the bottom one here. This is a bow tie. Common denominator. Now, the only thing I would say about this one is when you substitute, it's not real obvious at first that it's 0 over 0. So if I put a 0 in for x, I get 3 over 0, which we know that's bad. And then if I put a 0 in here, I get 1/5 minus 1/5, which is 0. But now think about this. 0 is the same as 0 over 1. Multiply fractions, you multiply across. 3 times 0 is 0. 0 times 1 is 0. So this really is 0 over 0. This looks a little different. Okay? So, that means we're going to need to do some algebra. Well, it's not a conjugate one. It's not a factor one. It's a common denominator. So we bow tie. So up here we get 5 minus x. Up here we get 5 plus x. And then the bottom would be this times this. Okay? And we're subtracting, and that's got parentheses. So this is going to be 5 minus x minus 5 minus x. So what happens with that? The 5s would cancel, and we'd have negative 2x on top, and then we would have this on the bottom, 5 plus x, 5 minus x. I don't really need to FOIL that out. Okay? So we end up with that. Now, what good does that do? I can multiply straight across. I get negative 6x, and then I get x times parenthesis times parenthesis. And now I can take an x out of the top and actually, I mean, they cancel, right? They cancel. And so what do I have? Now I can put my 0, right? So 5 times 5, so I get negative 6 25. Right? And the conversation we were having earlier, if you have 6x on top and an x on the bottom and you cancel the x's, that does not give you 5x, right? Right? It's not like you took away that. If it was x to the 6, that would be, no. There's one x on top, one x on the bottom, they cancel, and you have that. All right, last one here. Last one here, and I won't go all the way through this, but if you FOIL this all out and everything, it ends up being 8 plus 12x plus something x squared, I can't remember what, plus x cubed minus 8. So the 8's go away there. And then you have an x on the bottom. This is just like our problems with our h's. And so we'll take out an x. We get 12 plus, what was it? I think it was 6x, wasn't it? Plus x squared. And cancel, cancel. Now we can let x be a 0. And so we get 12. All right, so we got to FOIL out that 2 plus x cubed, FOIL it all out. The 8's go away. We can pull out an x. So that one actually is very much like the derivative ones. It's just the way they work, except we have an x there instead of an h. And that's where the h pulled out. And the way we go. I know that's pretty fast, but hopefully you picked up a little. If there was something you were confused on, you picked up a little something. And if you were confused still, then we'll talk about it. All right. So all right, get your calculators out. Get your calculators out. All right, so there's going to be a calculator part and no calculator part to this next quiz. Time could potentially be an issue on this one. It's one you're going to want to work. Probably if you have the calculator part and you get stuck, you want to maybe set it aside and no calculator back, okay, to it. You do, I think I've talked about this, but basically the rule on quizzes is you have to, once you start it, you have to finish it in that allotted time. So it's one class period, right? So when the bell rings at the end, you've got to be done as much as you're going to get to do. Okay, so hasn't been a real issue on any of the ones so far. This one for some people could be a little more, but anyway. So we're talking about limits. So we've done the algebraic. That was the worksheet. Those were good examples of all of those situations. What you might run into. Okay, and we've done the graphs. That was the pages in the book, and then plus that piecewise one was kind of a graph type one, so we want to be able to do limits there. And now I want to talk about using a table. Okay, so on the calculator, we've got this problem right here. So what I would like to do with this one is go ahead and graph this function right here. So we're going to do this limit, and I did put up this graph yesterday. I just kind of drew it by hand. So let's go into your calculators and let's graph x squared minus 9 over x minus 3. Okay, and I've got my version up here, so you guys go ahead and do that. Now, a hint on these, you might want to use a control, then the divide sign, which is a great way to put fractions in, because then you don't have to mess with parentheses. If you hit control divide. Especially when you get one that's got fractions inside of fractions, those common denominator ones that we're doing. Okay? Now, we're trying to do the limit of this one as x approaches 3. So as you're typing that one into your calculator, let's just remind ourselves of the one when we did this yesterday. What would we do if we weren't using our calculators right now to do this limit? What would we do? We'd factor the top. We get x plus 3, x minus 3. We would cancel the x minus 3's, which now would allow us to plug in our 3, and we would get 6. So the limit of this is 6. Now remember, a couple days ago when I wrote out the idea of limits, well actually it was yesterday, I said in words, this means what the y values are getting close to when the x values are getting close to a, in this case 3. So a limit is what are the y values getting close to when the x values are getting close to 3. Now we're saying that that is 6. Now if we try to plug in a 3 here, originally what do we get? 0 over 0. Let's try that on our calculator. Let's go to graph, or menu, trace, graph trace, type in a 3, and here's what you get on your Remember this yesterday? I drew it. There's a hole. There's a hole there. You can't see it on your original graph, but when you try to trace, I don't know, I'm not quite sure why they put that line there, but they're just showing you that at that point there's a hole there is what's happening. It's undefined. Okay? So let's escape out of that. So here's what I want you to do. Here's what I'm going to have you do on the quiz. Notice on those notes I said this is calculator tables. What I want you to do is look at limits, looking at a table of values. So let's think about how we've talked about limits. We can look at a graph. Where do the cars move? That's where the y values are getting close to. We can do algebra, right? Now that's not as visual, but we do the algebra and we can come up with the limits as well. We can also think about it. If what we're trying to find is what the y values are getting close to, as the x's get close to 3, what if we looked at a table of x and y values? That should show us too. And the calculator will let us do this real nicely. So what I'm going to have you do is go to Menu, go down to 7, which is Table. Okay? And notice it says Command T there, or on your calculator, it'd be Control T. That's how we can get that table. So from now on, instead of going into the menu, so everybody should be getting this on their screen now. It said split screen table. From now on, I'm just going to hit Control T. Whenever I want the table to show up, I'll hit Control T. If you hit Control T, it'll go away. Okay? Control T makes the table show up. Control T makes it go away. All right, now, you see here how it says undefined at 3? Right? But from this table, can you tell that the limit is 6? Remember we just said a minute ago the limit is 6. Can you kind of tell? Yeah, I mean, here to the left, these are the x values here. So when x is 2, it's 5. The y value is 5. When x is 4, the y value is 7. So it seems like it'd be in between. So it kind of seems like it's 6. But that's not going to be good enough. That's not going to be overwhelming evidence, which is what we want. So how can we get better evidence that the limit is 6? Get a lot closer to 3, like 2.99. So here's how you do that in your table. Does everybody's table look like this, by the way? Okay, be sure and let me know if it doesn't, because on our part of our homework today and on the quiz, I'm going to have you do this. You're going to have to actually write out your table that you're seeing on your screen. So let's go to our menu. Now notice you get this. Now let me back up a second. I've got a split screen going on here. Right now the table has dark black bars around it. If I would happen to click over here on the graph side and then go to my menu, I would get my menu options for a graph. I don't want that. I want to make sure my table is highlighted. And then when I hit menu, I get these options. Okay, so make sure the right thing is highlighted. All right, so now I'm going to go to number 2, table, and then go to number 5, which is edit table settings. So everybody needs to be able to go in here and change these settings. So we want to start our table not at 5, but we want to start it at 3, because this problem is as x approaches 3. So we want to start our table at 3. And our table step, so I'll just tab down there, we're going to make our table step be 0, 0, 1. Now most of the time 2 zeros is probably good enough, but you know, you might want to do, I tell you what, let's put 3 zeros. The only problem with 3 zeros is sometimes we can't see, the table widths aren't quite wide enough. But let's do 3 zeros just to be safe. Because you have to give your answers to 3 decimal places if they don't come out nice whole numbers. Like this one's going to come out 6, so we should be okay. So that's our table step. So we go ahead and hit enter. And now notice our table has changed. Now, I need to arrow up on my table at least one place, maybe 2. It's up to you. Okay? I want to get that 3 in the middle. Now, I don't have room to show 2 on both sides of the 3, two values. So arrow up 1 or arrow up 2, something like that. Now, do we have pretty convincing evidence that the limit is 6? Everybody see that? So the reason I'm having you do it all these different ways is I really want you to understand the concept of limit. Okay? What the y values are getting close to as the x values get close to, in this case, 3. So as the x, and here's your left on this side, and here's your right. Coming from the right of 3, coming from the left of 3. They're both coming in here to 6. Now what if this one would have said 3.999 right here? Yeah, what would be the answer? Does not exist. If this was 3.999, that would tell you from the left it's getting close to 4, and on the right it's getting close to 6. The two cars are not meeting. The limit would not exist. So in a table, we can tell the limit as well. We can see if they're going to meet or if they're not going to meet. In this case, we would say the limit is 6. All right, so I'm going to give you maybe 10 minutes, maybe a little more, we'll see. We'll do one together and then I'll maybe give about 10 minutes to work on part of your homework here. Now, the worksheet has 2 sides. We're only going to do one today. We're going to do the side that says calculator limits, the side that's facing up here. All right, so evaluate the following limits using your calculator. And so if I ask you that on the quiz, what I'm saying is give me a table, right? It might say justify using a table, that kind of thing. So let me show you what this is going to look like. So I'm going to go ahead and I'm going to click over here onto my graph side. You could get rid of the table right now if you wanted to and then bring it back. So if you want to hit Control T and get rid of the table. Oh, also, the tab key will open up your graph entry thing. So does Control G. Now that's 2 keys instead of 1, but Control G, if you want to hit that, will bring up your graph entry area. Okay, so I'm going to delete this one out of here, and I'm going to put in number 1 here. And what was it? Square root x plus 1, and arrow out of there. And then minus 1, and then tab down to the bottom, and then was it an X? Okay. And hit enter. Okay, and there's my graph. Kind of interesting, it kind of ends there at -1. Well, what's happening is, if you go to -2, and you'd have a negative inside your square root, so it would be undefined. So -1 is the last, so your domain here is from -1 to the right. You can't have any X's to the left of -1, or you'd have a negative inside the square root. Okay, but that's okay. What we're interested in is what the limit is as x approaches, what is it, say 0? Well, that would be right in here. Now, we could trace. Normally, I wouldn't even recommend you do this because that's not what this problem's about. But what's going to happen is if we trace at 0, sure enough, again, it's undefined, right? It's going to be 0 over 0. So what is that value there? So I'm going to get my table back up. So Control T. And I could have left the table up the whole time. Okay? But the problem now is, what? What do I need to do now? I need to go to my table settings, right? Now, where do I get that? Menu, number 2, table, number 5, edit table settings. I want my table to start at, where do I want this one to start? We started at 3 on the last one. This one we started at 0. Now, if you left your table up there, it's still starting at 3. I got rid of my table, and then when I came back, it's now changed those settings. So if you leave the table up, it's probably a better idea because then it'll keep those same settings for you. So I'm going to start at 0, and then I'm going to go 0.0001. 3 zeros is probably good. And then I better arrow up. Now notice, you're getting scientific notation. Now, keep in mind, what you have to do now on your worksheet is you have to copy down this table. Okay? The X column, the Y column. Now, what do you think the answer is here? 0.5. Exactly 0.5, I would agree. And so 1/2 or 0.5, I don't care, fractions, decimals, fine. But that's not even the most, but I want the evidence. So on the quiz, I will have you copy down the table. As a matter of fact, I may not even ask you on the quiz what the limit is. I might even tell you. I might say the limit, like on this worksheet, I might do the limit of equals 1/2. Prove that with a table, right? So I'll just tell you that it's going to be 1/2, but I want to see your table. Now, don't put in 1, -1, e -4. Don't write that. That doesn't mean anything. Right? That's scientific notation. What it means is 10 to the -4. So it's -0.0001, okay? And that's 0.500001. And then I got 0, that's undefined. Then I got 0.0001, and that's 4.9998. And I got 0.0002, and that's 0.49997. 3 9s and a 7. That's what I want to see on your paper. And that's the evidence right there that that limit, the y values are approaching 0.5. Okay, I'll give you about 5-10 minutes here to do a few more on that page. We just make sure we get the hang of working our calculator and making that happen. Okay, so at number 2, remember you're supposed to be accurate to 3 decimal places. So number 2, what do you have? -0.416. I think it actually is 666 repeating. It's not important that you go out that many or know that, which is like 5/12, I think is the actual answer. But this is fine. 3 decimal places is good. Okay, so if you can get the 3rd decimal place to agree, right? Now in this one they kind of do agree. I mean you got 500,499. That would round. You can tell it's going to be. It's going that 3rd decimal place. You tell it's going to be 0.5 exactly. Okay, you have 1 more minute. You can stand up and stretch, or you can work on your worksheet for 1 more minute. All right, time's up. So let's please set that aside, and I know you're probably right in the middle of one, but just keep it on your calculator, and you'll be fine. Get your notes back out, probably. We're gonna kind of switch gears here just a little bit. Okay, because I'm throwing a lot at you here, I know, and that's one of the reasons I wanted to review this at the beginning of the day, kind of give you the big picture of what's happening here and what all we're doing. I want to come back to that here a little bit, look at the big picture a little bit. So I wanted to, before we switch gears, I wanted you to get you a chance to work on a few and kind of get that hopefully figured out a little bit about what you're doing. All right, so if we look at what we were talking about here, we said we started the chapter 2 with these derivatives, this idea of the derivative, building on what we learned in chapter 1 with the chart and slope and what that means, f prime. We learned this new formula for the derivative. It had a limit in it. We used that to come up with a nice little shortcut rule for some easy power type problems. And then we said, let's investigate this limit idea. So that's what we've really focused on the last couple days. So now we should have been through all of this. We've looked at graphs to do limits. That's where we look to see if the cars meet. We've now looked at tables on our calculator so we can tell where the y values are meeting and like the cars meeting. We looked at some equations where we do some algebra to them and we figure out what the limit is. And these are the different possibilities when we do that. Okay, so we've kind of been through the whole gamut now of limits and what can happen. All right, so what we want to do is we now want to come back. So we're off that little side trip into limits, and we're now back to this idea of derivatives, the chart, how that all works like it did back in chapter 1. Local max, min, increasing, decreasing, those kind of things. Okay, so kind of get our minds organized here a little bit for what we're talking about. So I put this up here on the board. If I had a function f and it was 3x squared and I wanted to do the derivative, so that's the arrow going down, we said we're going to call that f prime. That's the derivative. Well, we learned a nice little shortcut for that, and the derivative of 3x squared is 6x. And if I want to do the derivative of that, the derivative of f prime, that is f double prime, and the derivative of 6x is, does everybody agree with me that that's 6? Okay, I was explaining to a couple people here earlier, so we talked about it last period. I want to make sure that everybody knows that because these to me are the easiest ones of all. If I have this, so I want to make sure everybody seems easy. If I do the derivative of x cubed, it's 3x squared. Derivative of 8x is 8. I mean, that one should be one that we can say just almost faster than any other derivative. Now, I know some of you are getting hung up on it because you're trying to do the power rule. You're saying, well, there's a 1 there. I bring the 1 down in front. 1 times 8 is 8. Then drop that to a 0. Wait a minute, is that 0? No, that's 1. 0 power. Don't think of it that way. Just think, hey, 8x is like a line. The slope of 8x is 8. So whenever you see 8x, 7x, 2x, the derivative is simply the number that's in front of the x. That's it. Now, if it's x to the first, right? If it's x to another power, then, of course, you got your whole power. So those should be real easy. And then what's the derivative of 3? 0. Whenever you have a constant, that's the easiest one of all. You have a constant all by itself, derivative of that is 0. Okay, so anyway, off that. So here we go. So we got f prime, we got f double prime. Now, not quite sure why the book puts it here, but there's probably no other good place to put it, so we might as well talk about it here. What would we call it? Basically, this is just a notation thing, so I don't want you to freak out about it. I don't want you to get too hung up on it. It's not that hard of a concept. It's just a notation thing. It's just a terminology and a notation thing. What would we call it if we went backwards? If we do this, the act of going from f to f prime is taking the derivative of the function. The act of going from f prime to f double prime is taking the derivative of the function. Well, doesn't it make sense that we could have a name for the act of going in reverse? Think of it like FOIL. In my algebra class, we're doing that right now. When you factor a trinomial, you're doing FOIL kind of in reverse. And that's what we're talking about in algebra class right now. Well, that's what you're doing. And here's the name. It's not fancy. It's the antiderivative. So when we go in reverse from f double prime to f prime, or from f prime to f, that is called taking the antiderivative. Now, we're not going to work very much on those right now because we've just started doing derivatives. It's kind of like, again, in my algebra class. We spent chapter 9 in my algebra class doing FOIL problems. And I told them we've got to get really good at FOIL problems before we can start then doing the factoring, doing it in reverse. Well, we want to get a lot better at doing derivatives before we start worrying about going in reverse. Okay? But let's just do one here. So and here's where the notation comes in. So the idea now is, what if we started with a function f and wanted to do its antiderivative? Anybody guess what it is? Something x cubed. I think it's just x cubed, right? Now, how can you tell? The power has to be one higher, you know that. And then just check it, right? I mean, think about when you factor. When you factor something, how can you tell if you did it right? You do FOIL and you check it, right? If you're doing it backwards, how do you tell if you did it right? Do it forwards to see if it gets the same thing. So x cubed, oh yeah, do the derivative, that's 3x squared. So you could check it by doing that, yes. Great question. We'll get to that later. Yes. Here. Remember that thing? Well, no. Well, let's talk about it now. That's a good point. Remember we said if you have the f prime graph, and you go to the f graph, remember when we did those? Weren't we doing the antiderivative, right? We didn't call it that, but that's what we were doing. And we said we don't know where it is. There's some vertical shift. So technically, when you do an antiderivative like this, here's what you'll do. You'll put a plus c on it. C for some constant. And you'll say, whenever you do an antiderivative, you'll stick on this plus c at the end, and you'll say, there might have been some constant here, like a plus 6. We don't know. Because when you do the derivative, it goes away. Okay? But again, I'm not going to worry about the process of doing antiderivative right now. We're not really going to get into that. All I want you to know is, what are we going to call it? I mean, if we go from f double prime and go backwards, we know f double prime would turn to f prime, and f prime would turn to f. But what do we call this one if you go backwards? We're going to call it capital F. Now, for some of you, that's going to be a problem because I've noticed that your f functions, when you draw your f, you've been drawing capital F's. We've got to be careful because the f, little f, and big F now for us have two different meanings. Okay? So from now on, big F is the antiderivative of little f. Now what that means is what's big F prime then? That's little f, right? Big F prime is the same as little f, because that's what this is saying. If you have big F, you do the derivative, takes you to here. Do the derivative of that, takes you to there. So big F prime is the same as little f. Now, big deal. It's just a notation thing. So one of the reasons when I made my chart, and you guys might remember me talking about this a little bit, when I made this chart, I didn't label the left side over here. Well, that's because you might be working on a situation where you want this to be F, F prime, and F double prime, or you might be working on a situation where this row is big F, this row is big F prime, this row is big F double prime, but what did we just say big F prime is? Little f, and then this would be little f prime. And I will always say little f. If we just say f, we're talking about little f. If we're talking about capital F, we can say big F, okay? But so you just need to know that connection. What's going to happen on the homework? We're going to practice by reviewing some stuff from chapter 1. So what they're going to do is, instead of like in chapter 1 where they gave you an f prime graph and then ask you questions about f, they're going to give you an f graph and ask you questions about big F. It's the same thing. It's doing the same thing. If they give you a little f graph, those are the slopes. Those y values are the slopes of big F. So if they give you a little f graph and ask you questions about big F, it's the same chart stuff we did on the last test. So there's going to be some of those on the homework. Okay? And here's the other thing that's going to be on the homework. And this is on page 121. And it is problem number 19. Now, you're going to do one just like it for the homework, so why don't we let's work this one together. You're going to do number 21, I believe, which is just like this one. So you can kind of mimic this one when you do number 21. Okay? All right, so on problem 19, so this is the first of what will be many times you work problems like this. This is a very fundamental, you might say basic calculus problem using the chart. Now in chapter 1, all of our chart type questions came from graphs, okay? And so typically where we had an f prime graph. So here's what number 19 is asking. Number 19 has 4 parts. They have this function and they want to know where is f increasing, where is f decreasing, where does it have a local max, where does it have a local min. Now in the directions it says give all your answers exactly, like square root of 3. What that is kind of code for saying no calculator. This is a no calculator problem. Because let's face it, if this was a calculator problem, we could graph that graph, we could see where it has a local max, see where it has a local min, we could see everything. You're not allowed to do that, right? We're going to use the calculus ideas that tell us where these things are. So most of the time, a problem like this would be a no calculus. Okay? So, let's think about how we did these problems when we had graphs. Usually when we had these problems, we were given an f prime graph. Let me draw that in red over here. We were usually given an f prime graph of some kind. And it might have looked like, this or something like that. Okay? And this was f prime. Now, what did we care about when we looked at an f prime graph? We cared about those points right there. Because if we wanted to know where f's increasing, what do we need? F's increasing when f prime is positive. So we need to know when is f prime, we needed to know when f prime was positive. Well, it's when it's above the x-axis. That was easy. We just looked at the graph, saw where it crossed. We could see where it's negative, see where it's positive. How are you going to tell where f prime is positive, negative here? Well, first of all, we need f prime. We don't have a graph. We don't have a calculator. But we do have a handy-dandy shortcut that we've learned, right? So what's f prime? 3x squared minus 6x. That's f prime. So what we would like to do now is figure out when that equation is positive. Boy, when we looked at the graph, it was sure easy. We could just see when it was above, when it was below, where it crossed. That was all easy. How are we going to tell when this is positive? Find the zeros. Now, somebody in their class earlier, they said, well, let's plug some numbers in. Well, what's wrong with that? It could take a while, right? And you never. The real problem is you never know when it switches from being positive to negative. And isn't that what we need right here? For local max, we need f prime to switch from positive to negative. Well, where's that going to happen? When it is 0. So what you need to do is you need to put equals 0 here. I can't emphasize this line enough. Write that down. And every time you do one of these problems, you get a point for having that on your paper. You've got to have that on your paper. Okay? Now, how much algebra work you show is kind of dependent on how much you need to show, but you get points for showing these steps. All right, so we need to solve this and set it equal to 0. What's that called when you find out when f prime is 0? Yeah, but no, I mean in calculus. What does it mean when f prime is 0? That's called a stationary point. What we're finding are the stationary points. But what we need to do right now is, now we're doing algebra. Factor out a x or a 3x. Either way would be fine. And so we get x minus 2 equals 0, right? And then the zero product property says, all right, if you've got two things multiplied or multiple things multiplied that equal 0, one of them has to equal 0. So either 3x is 0 or x minus 2 is 0. Now, how much of this you write down is kind of up to you, right? So we know here we're going to get x equals 0 or x equals 2, right? If I could have skipped maybe an in-between step there. But you certainly have to have this line right here. Matter of fact, you'll hear me say this multiple times this year. If you don't know what to do in a problem, do the derivative and set it equal to 0. That's usually a good place to start. Do the derivative and set it equal to 0. Because go back to what we learned in chapter 1 with the graphs. Knowing those places where it crossed were key to knowing what was going on. All right. So now, that's where it's 0. But remember, what we want is we want to know where f prime was positive or where it was negative. So what we want to do is plug in some points before and after those. Now, a great way to organize your work is to do this. And I'm going to call this an f prime number line. So you'll hear me say, draw yourself an f prime number line. So what you do is you take your stationary points. Matter of fact, I might even label those here, because sometimes the problem asks for your stationary points. So x equals 0, x equals 2 are stationary points. I'm going to draw myself a little number line here. I'm going to put 0 on it and 2 on it. And what we would like to do now is plug in some values. Now, where am I going to plug them? Into f prime, because we're trying to figure out if f prime, that's why I labeled this f prime, to remind myself that's where I'm going to plug these in. So, -1 would be a number on this side, 1 would be a number in between there, 3 would be a number over here. So I'm having to do more work than we had to do back in chapter 1, because when we could just look at a graph, we could see where it was positive or negative. Now we've got to actually do some calculations. All right, so I'm going to take my -1 and plug it into f prime. Now, I would plug it into the factored version. I think that's a little faster. Don't have to. Remember, all we care about if it's positive or negative. We don't care what the value actually is. So when I plug a -1 in here, I could say 3 times -1, that's negative. -1 minus 2, that's negative. Negative times negative is a positive. And I just put a little plus sign there to mean positive. A 1, put it into there. 3 times 1 is positive. 1 minus 2 is negative. Positive times negative is negative. Put a 3 in. 3 times 3 is positive. 3 take away 2 is positive. Positive times positive is positive. And doesn't that show me everything that my old f prime graphs from chapter 1 used to show me? The same stuff. It tells me when the f prime graph's positive, when it's negative. Now, what if you had a flat spot? What would the number line look like? What would happen in your number line if there was a flat spot? Positive and then stay positive, right? It'd be going up, then continuing to go up. If it went positive, then positive, you knew you had a flat spot. Okay, it'd be kind of like this graph bouncing off of it. All right, so let's go to our questions. When is f increasing? From negative infinity to 0, and from 2 to infinity, because that's over here when f prime is positive. When is f decreasing? Between 0 and 2, because that's when f prime is negative. Okay, now, pay careful attention to this. When it asks for a local max, that's where on this one? At 0. Because that, and here's what you have to write, because I didn't ask for this on our last quiz, because we were just getting started with it. But most of the time, when you're asking local max or min question, it's going to say justify why it's a local max. And so what you have to say here is what I have in red. You have to say because f prime switches from positive to negative. At the very least, that's probably good enough on the AP test. You know, you could write out the words positive and negative, but you have to have that on your paper. They specifically talk about that in the that handout I gave you at the beginning of the year. When you're doing local max min problems, they want to hear this. And then, of course, your local min would be at x equals 2. And again, you would have to say, because f prime switches, right? F prime switches from negative to positive is why that's local max. But see what that looks like now? So when we have an equation for f of x, instead of a graph, we can find f prime with our shortcuts. We can find our stationary points, which would be where it crosses the x-axis by setting it equal to 0. We can solve it. Those are our stationary points. We can put those on a number line, check points in between. That tells us when it's positive, negative, which is all the information we used to get off that graph. Now, what we don't have yet is what if you wanted like concave up? Where is f concave up when f prime is increasing? Do we have any information here about when it's increasing? No. So we would have to go, when is f prime increasing? Well, when f double prime is positive. So what we would have to do is do a second derivative. For concavity, we'd have to do a second derivative.